Okay, so to model a scenario, as a game, as a static game of complete information, we need three things. One is, who are the decision makers, basically who are the players. Okay, so we can name them one and two. Okay, so set of players are basically, the two roommates. Okay, and the second thing that we need is what can those players do. Okay, so you can imagine that these players can actually do some contribution, to buy the public good. Okay, so we can have a scenario like this, that the action set of player one, or basically you can also call it a choice set of player one, is he can contribute anything from 0 to m1. Okay, so you can imagine that m1 is kind of the pocket money of roommate one, or you can say his income. So he cannot contribute more than what he earns. Okay, so basically his action set is a closed interval, 0 to m1. Okay, and you can imagine that player two's action set is also a closed interval from 0 to m2. Is that fine? Okay, where m1 is, you can imagine it's an income of consumer one, or basically roommate one. m2 is the income of roommate two. Okay, is that fine? Okay, good. Okay, the third thing that we need is basically the payoffs, the utilities. So you can imagine that player one is going to pick an action from his action set. Player two is going to pick an action from his action set, and then uh, that pair of actions, you can call that action profile if you wish. That action profile will determine the payoff to player one and player two. Okay, so utility of player one is a function from a1 cross a2 to r, and utility of player 2 is also a function from a1 cross a2 to r. Okay, so why is utility of 2 a function of player 2's action, player 1's action? Because if player 1 is going to contribute more, that's going to positively affect player 2. Okay, similarly, player 1's utility is also a function of the action taken uh, by player 2 because of the same reason. Okay, so this is the standard public good contribution game. Okay, so we can assume some utility form to actually solve this problem. Okay, so let's just consider the following. So suppose utility of player 1 is a function of c1 c2, where c1 is a contribution of player 1, c2 is the contribution of player 2. Okay, and let's assume that if player 1 contributes c1 and player 2 contributes c2, so the total contribution is c1 plus c2, and with that total contribution, we are going to buy some amount of public good. Okay, is that okay? We are going to buy some amount of public good, and let us say the utility to the individual is 2 square root of c1 plus c2. So let's assume some quasi-linear utility. Okay, plus m1 minus c1. Okay, so it's linear in the amount of money that the individual is consuming. Okay, and basically it is non-linear in the amount of public good consumed. Okay, so this is the total amount of public good consumed. Okay, and this is the utility form. We can assume this, just to solve the problem. Okay, so we can also do the same thing for player 2. Okay, let's assume that players are symmetric in the sense that they have identical pair of functions. Okay. Okay. Is that clear? Okay. So we'll solve this problem. Okay. And you know, M1 and M2 are given. Okay. So M1 and M2 are exogenously given. So maybe we can just right now solve this problem for some specific value of M1 and M2. Otherwise, we can also solve this particular problem for, you know, taking M1 as M and M2 as you know, variables, and we can actually find Nash equilibrium as a function of M1 and M2. Okay, so in that case, you know, you can later on just plug in M1 and M2 and figure out what is the Nash equilibrium for different values of M1 and M2. Okay, so I mean, let's just do that for some specific values of M1 and M2 first, and then, you know, you can try for other values of M1 and M2, and then you can try and figure out what is the relationship between Nash equilibrium and, you know, different possibilities of income levels of the two consumers. Okay, fine. Okay, so maybe let's assume that, you know, both have the same amount of pocket money, which is 10. Okay, fine. Now let's solve this problem. Okay, so this is the public good contribution game. Okay, and now we are going to solve for Nash equilibrium. Okay, is the game clear to everyone? Okay, so if you know, if you've seen the earlier examples, you know, the way we approach this kind of problem is we can actually find the best response function first. Okay, best response of player 1 as a function of player 2's contribution, and similarly best response of player 2 as a function of player 1's contribution, then try and figure out the Nash equilibrium. Is that okay? So we'll you know, use the same approach. Okay, is that fine? Okay, so let's do this. Okay, so how do so if you want to figure out the best response of player 1, okay, then the problem that you will be solving is maximize with respect to C1, okay, 2 root C1 plus C2 plus, so since M1 is 10, I can write it as 10 minus C1. Okay, and the constraint is that, of course, you cannot choose an action, you know, outside the action set. So obviously, which means that C1 must be between 0 and 10. Okay, so you solve this problem. Okay, and then you will get you know, the optimal value of C1 as a function of C2, because when you're solving this problem, you are holding C2 fixed. You know, you are taking C2 as given. Okay, you are only choosing C1. So whatever solution you're going to get will be a function of C2. Is that clear? Okay, so that's known as best response function. Is that clear? That's known as best response function. Okay, so let's solve this problem. Okay, so how do we solve this problem? You know, what we can do is we can take the derivative of the objective function, okay, and see how the function looks, and then we can use it to actually you know, figure out the optimal value of C1 as a function of C2. Okay, so let's take the derivative of this. Okay, so what is the derivative of this? 1 upon root C1 plus C2 minus 1. Is that okay? That's the derivative. Okay, I mean, you can easily see anyways, this is actually a concave function. Okay, and this is the derivative. Okay, so now, you know, if C2 is kind of, you know, just imagine C2, if C2 is greater than 1, you know, what will happen if C2 is greater than or equal to 1? Notice that if C2 is greater than or equal to 1, in that case, this term is negative. Do you agree? No matter what C1 is, this term is always negative, because if C2 is greater than or equal to 1 and C1 has to be greater than or equal to 0, so this term will be greater than 1, greater than or equal to 1. Do you agree? Yes or no? The denominator will be greater than or equal to 1. And since the denominator will be greater than or equal to 1, this 1 upon something greater than or equal to 1 will always be less than or equal to 1. Okay, so this term basically is less than or equal to 0 if C1 is greater than, sorry, if C2 is greater than or equal to 1. Right? If C2 is high enough, this term is less than or equal to 0 for all values of C1. Yes or no? Okay. Now, what does this tells you about the optimal choice of player 1? What do you think? So, what does this tells you about the optimal choice? You know, what do you think? How much should player 1 contribute? You know, so I'm asking this question. Tell me what is BR1C2 if C2 is greater than or equal to 1. What is the best response of player 1 if C2 is greater than or equal to 1?
0.
0.
Very good. Very good. It's a unique best response, which is to contribute nothing. Is that okay? So this is 0. The reason is because, as you can see, the derivative is negative, so that means the benefit of contribution is marginal benefit of contribution is negative, no matter what amount you contribute. Okay, so that means you wouldn't want to contribute at all, right? I mean, you don't want to reduce your satisfaction level, you don't want to reduce your total benefit by contributing more, right? I mean, so that's the reason, you know, this is just going to be 0. Okay, now the other possibility is C2 is less than 1. Okay, so that's the second case. You know, I mean, C2 can be either more than 1 or less than 1. So if C2 is less than 1, what do you think? In that case, what are you going to do? So if C2 is less than 1, notice that when C1 is 0, this term is positive. This term is positive, right? When C1 is 0, C2 is less than 1, then this term is basically this whole term is positive at C1 equal to 0. Do you agree? So that means at C1 equal to 0, the marginal benefit is positive. Do you agree? Of contribution. So that means you would want to contribute. You know, you would want to contribute. You wouldn't want to contribute 0. The reason is contribution is rewarding. Okay, so you will keep on, you know, increasing your contribution till, you know, this term becomes 0. Is that okay? So if C2 is less than 1, in that case, the solution will be given by this equality. Is that clear to everyone? Yes or no? Is that fine? Okay, so what are we going to get when we are going to solve it? Tell me, what are we going to get when we are...
Sir, sir, so here if we have put it equal to 0, because if the person if the derivative is like if C2 is less than 1, then if the person increase C1, then he will receive some extra marginal benefit, and he will like to contribute until that marginal benefit become equal to 0.
That's right. So he would keep on contributing till his marginal benefit becomes 0.
Got it, sir. Got your point.
That's it. You know, absolutely. That's the right. That's the point. Okay. So if you just solve it, what are we going to get? What is the optimal contribution? Tell me.
C1 equal to
Solve.
1 minus C2.
Sorry.
C1 equal to 1 minus C2.
That's right. Absolutely. Okay. So there is a unique best response, which is 1 minus C2 if C2 is less than 1. Okay. Now, because this is a symmetric problem, so we don't have to do this again. We can straight away write the best response of player 2. Okay. It will be 0 if C1 is greater than or equal to 1, and it will be 1 minus C1 if C1 is less than 1. Okay. Okay. So what is the next step? We are going to plot the graphs of BR1, BR2, okay, and figure out the Nash equilibrium. Okay. So let's just do that. Okay. So what is the graph of BR1? The graph of BR1 is C1, C2 such that, okay, C1 belongs to BR1, C2. Okay. Similarly, graph of BR2 is C1, C2 such that C2 belongs to BR2, C1. Okay. Now all that you have to do is, the intersection of these two graphs will give you the Nash equilibrium. So you just have to plot these graphs, in R2 plus, okay, and you'll get it. Okay. So well, yeah. So in actually 10 by 10 box, okay, because action set of player 1 is 0 to 10, action set of player 2 is 0 to 10. Okay. So you just have to plot this. Okay, so let's plot it. Let's first plot graph of BR1. Okay. Okay, so if C2 is greater than or equal to 1, so this is 1. Okay. So okay. So if C2 is greater than or equal to 1, the best response of player 1 is to choose 0 units of C1. Okay. So if C2 is greater than or equal to 1, C1 is 0. So I'll get this. Yes, because whenever C2 is greater than 1, the best response is 0. Okay. And when C2 is less than 1, the best response is 1 minus C2. So what that means is you're just going to plot a 45-degree line like this, right?
Yes, sir.
Okay. And then that's it. This is a graph of BR1. Okay. This is,
Sorry, sir. Can you please explain this part again?
yeah, just a minute. So this is graph of BR1. Okay. So yeah, so what I was saying is that if C2 is greater than 1, so whenever C2 is greater than 1, the optimal choice of C1 is 0. So I've just for each of these values of C2 between 1 and 10, I have just considered C1 equal to 0. So I've just plotted those points, those pairs, 0 comma C2, such that C2 is greater than or equal to 1. Okay, so that's going to give you this line. Okay. And then when C2 is less than 1, then you're just going to plot C1 equal to 1 minus C2, which is nothing but a line segment C1 plus C2 equal to 1. Okay, from 0, 1 to 1, 0. Is that okay? That's all that I've plotted. That's it.
Got it, sir.
Okay. Now, what you're going to do is this, that you're going to also plot BR2. Okay. So how do you plot BR2? Just exactly the same way. So I'm not going to repeat it. You can just try this on your own. I'll just straight away make the graph. Okay. And you just verify this, that this is exactly how it's going to look. Is that okay? Fine. And, check that this is where the overlap happens. Yes or no? This is the intersection, right? These are all the intersections. So basically we have multiple Nash equilibria in this case. So let me write the set of Nash equilibria. So set of Nash equilibria is C1, C2, Okay, so if you want, you can write it. You can write that this is 0 to 10 cross 0 to 10. Okay, such that C1 plus C2 equals 1. Is that okay? These are the set of all Nash equilibria. Is that fine? So C1 has to be between 0 and 10. C2 has to be between 0 and 10. And this equation must also be true, that C1 plus C2 is equal to 1, because that's where the intersection is. Okay. Have you all understood this?
Yes, sir. I totally understood.
Any questions? Okay, let me ask you this question. Is this Pareto efficient? Okay, let me give you one Nash equilibrium. So just think about half comma half. Half comma half. Do you agree half comma half is a Nash equilibrium? Okay. Now my question
Yes.
is half comma half Pareto efficient? You remember Pareto efficiency? Okay.
Yes.
So is there a way to improve the satisfaction level of one of them without reducing the satisfaction level of the other?
Sir.
Yes.
Sir, so here C1 plus C2, that term will be anyways be 1. So we can keep that as 2 plus, so it would be 10 minus C1 ultimately, which we will be getting. And for the other person, it will be 10 minus C1. If we try to, if the person increase C1, if one person increases consumption of the public, like his contribution to the public good, then the other person will be decreasing the contribution. If C1 increases, then C2 will automatically decrease to keep that equal to 1. So if one person is becoming worse off, like if he person one increase C1, so he will become worse off. Other one is becoming better off. So this is Pareto efficient.
Okay. Well, okay. So basically, I'm not. So remember, the definition of Pareto efficiency doesn't say that you have to only pick points from the set of Nash equilibria to compare them. So what you are doing is basically you are looking at a Nash equilibrium half comma half, and you are basically checking if there is any other Nash equilibrium which can improve the satisfaction level of one without reducing the satisfaction level of the other. Now that's not the definition of Pareto efficiency. The definition of
Got
Pareto
it.
efficiency says, is there a feasible way? So basically, what do you mean by feasible? So can they pick different actions compared to, let's say, half half, and is it possible to improve the satisfaction level of one of them without reducing the satisfaction level of the other? Now I'm
Yes,
not
sir.
imposing any
Yes.
restriction that particular
Got it.
action pair has to be a Nash equilibrium. I'm not imposing that kind of restriction. So the question here is this: can they choose differently? May not be in an equilibrium sense.
Yes.
As long as it's feasible, it's fine. Can they choose their actions differently in such a way that you can raise the satisfaction level of one without reducing the satisfaction level of the other? So that's a question.
Yes. Yes, sir, got it. Sir, so if both of them contribute 1, then the utility of each is coming to be 11.8. And if when both were contributing half, then it was coming to be 11.5. So both will be becoming better off if they both contribute 1. So that
Okay.
will be.
Okay, so you can actually, because both of them are symmetric, so you can actually check, if there is some symmetric uh, action pair, which can improve the satisfaction level of one. Because if it can improve the satisfaction level of one, it will also improve the satisfaction level of the other. So U1 half half is basically, this is the Nash equilibrium choice. So U1 half half is uh, 2 times square root of 1, which is 1. Okay, so 2 times 1 plus 10 minus half, okay, which is what? 12 minus half, which is 11.5, right? Okay, now what is U111? Okay, let's see. U111, well, that's going to be 2 square root of 2. plus 10 minus 1, which is 9. Okay. Now notice that square root of 2 is definitely bigger than 1.4. Do you agree?
Yes.
Okay. So you are going to get what? 9 plus 2.8, which is 11.8. So 1 is actually Pareto superior action pair compared to half. Is that okay?
Yes.
Okay. So I mean, so Nash equilibrium, of course, may not be Pareto efficient. I mean, you have also seen that in Prisoner's dilemma case. Uh, the only Nash equilibrium, in fact, Nash equilibrium in the Prisoner's dilemma, Nash equilibrium is the only action profile which is not Pareto efficient. Okay. All the others are Pareto efficient, actually. I mean, if you just recall Prisoner's dilemma. Okay. So I mean, Nash equilibrium may not be Pareto efficient. I mean, this is one very important thing. Okay, especially in public good scenarios. I mean, uh, because when individual takes a decision, he only cares about the benefit that his contribution will have on his own satisfaction level. Okay, he doesn't really take into account the positive externality of his decision on the other player. That is why it leads to under provision of public good. Is that okay? Clear to everyone?
Yes, sir. Clear.